All right, guys. So section 2.11. Okay, more about logs. So because log functions and exponential functions, again, are inverses of each other, the characteristics of their graphs will also have an inverse relationship. Okay, so everything that is happening in exponentials will be inverted for logs. Okay, so a log function has this general form. We already went over that in section 2.10. Okay, where a, b are constants and a cannot be 0, and we went over why b cannot be 1. And of course, b has to be greater than 1. And if you look at the graph of a basic log function, it kind of looks like this. So as long as there's no transformation, when a is greater than 0 and b is greater than 1, this is the big difference between these two, your domain, I know you can't see this, but your domain is parenthesis from 0 to infinity, and this is a parenthesis. And your range is going to be from negative infinity all the way, so from 0 to infinity is your domain, and from negative infinity to infinity would be our range. And that's also going to be the case, right, from 0 to infinity, and from negative infinity to positive infinity, even if a is less than 0. So if a is negative, because remember, when a is negative, it's just a reflection over the x-axis. So this bottom part right here, so this bottom part flips up, and the top part flipped down. So this is still a log function, still a log, even though it looks slightly different. So let's go back and review increasing versus decreasing, right? So this guy right here, log functions are always increasing or they are always decreasing, similar to exponential functions. They will never switch from one to the other. Like a parabola, right? Goes from decreasing to increasing. Or a quartic function, right? Or a cubic function, increasing, decreasing, increasing, back and forth. So they will never go back and forth. They will always either be increasing or they're always decreasing. They will never switch. So they will never have a local extrema, unless it's on a closed interval. So unless they say, from this point to this point, then they have an absolute min and an absolute max. Now, in terms of concavity, concave up versus concave down, log functions are always concave up, like this guy, right? Or they are always concave down, like this guy. They will never switch concavity either. So they will never switch concavity, so they have no points of inflection. And they will never switch from increasing to decreasing, so they have no relative extremas. Next part is about the end behavior. For log functions in general form, as the input values increase, so as the x's increase without bound, the output values will increase or decrease without bound. Okay, so if we look at this one, what is the limit as x approaches infinity of f of x? Well, that's going to be infinity. And for this one, what is the limit as x approaches infinity of f of x? It's going to be negative infinity. Since log functions have a restricted domain because they start, right? They start at 0. They are vertically asymptotic to x equals 0. As a result, the left end behavior will occur as x approaches 0. We're not going to say limit as x approaches negative infinity. This is going to be a common mistake because when they ask for left and right end behaviors, right, the left one for logs is very, very different than it is for any other function. You have to say it approaches 0 from the right. So we are approaching 0 from the right. And where is it going? And of course, it will go to positive or negative infinity depending on what the a value is. So these are all the behaviors and the definitions that you need to know about the characteristics for graphing log functions. So let's put that to the test. Write a limit statement for the end behavior for the following log functions. So here, the limit as x approaches 0, right? So as I am approaching 0 from the right of f of x, where am I going? To negative infinity. And for the right end behavior, you have to write as x approaches infinity of f of x. So as we're going this way, what's happening to the y values? Infinity. So for left end behavior, if you write the limit as x approaches negative infinity, you are going to get marked wrong. So do not write that. Okay, for log functions specifically. You have to say as the limit approaches 0 from the right of f of x, this guy is going to infinity. And as x approaches infinity, for the right end behavior of f of x, it's going to negative infinity. Now for this one, I know you can't read it, so I'm going to rewrite it. This one is supposed to say g of x is equal to 2 log base 3 of x. So because you notice that a is greater than 0, and of course b is greater than 1, you know kind of how this graph looks like. It does not have to be perfect, but I do know that it's going to look like a typical log function. So you do a rough sketch, just like I just did, and then you can see that your left end behavior, which you have to write as x approaches 0 from the right of f of x, is negative infinity, and the limit as x approaches infinity of f of x is positive infinity. Example 2, for each of the following, determine if the log function is increasing, decreasing, and if it's concave, up, or down. So we're going to look for increasing or decreasing, and then we're looking for concavity, up or down. So looking at this function, you always read it from left to right. So obviously this guy is decreasing, right? This guy, as x grows, so does y, so that's increasing. And for this one, you're going to have to do a rough sketch before you figure that out. So just to I know the formatting came out funny, but h of x is equal to negative 4 log base 6 of x. That's what it's supposed to say. So it looks like a is negative and b is greater than 1. So a rough sketch, I know that from the initial definitions, when a is negative, it is a reflected log function. So it kind of looks like this. I don't need to know exactly how it looks like. So obviously this guy is always decreasing. Now in terms of concavity, well, that's concave up. Okay. This guy is going to be concave down, and this one is concave up. All right, selected values of several log functions are shown in the table. For each table, find the value of the constant k. So they're telling you that this guy is a log function. So if you remember from section 2.10, right, for log functions, which one is additive and which section is multiplicative? So hopefully you remember that the x is multiplicative and the y is an additive. So that means you're adding to go from 1 to 1. And that's what we see, right? Plus 1, plus 1, plus 1, plus 1. This guy is plus 5, plus 5, plus 5, plus 5. So they're telling us that this is a log function, so it has to follow. This is minus 10, minus 10, minus 10, minus 10. And this one is plus 7, plus 7, plus 7, plus 7. So the second part of this definition is the fact that the x values are a multiplicative x value. Okay? But in this function, there is going to be a transformation. So looking at these functions, hopefully you see that the x values are powers of 2. Okay? So going from here to here, this is times 2. Going from here to here, this is times 2. Okay? So I have enough information to know that it's multiplicative of 2. So 2 to the 0 is giving me 1. 2 to the 1 is giving me my 2. This guy is 2 cubed. This guy is 2 to the 4th. So k should come from 2 squared. Okay? So because this is times 2, I know that 2 times 2 is 4, or 2 squared is going to be 4. So k is going to equal 4. So the reason why it's important to know the base value of each of these numbers is because this is going to tell us that this is coming from a log base 2 function, but we'll get to that. Okay? All right, next up, since k is the first value, I'm going to work backwards to figure out what's happening. All right? So hopefully, or just go from here. So 6 times what is 18? Times 3. 18 times 3 is also 54. 54 times 3 is also 162. So going backwards, obviously I have to divide by 3 to get k. So k in this case is going to be 2. All right? But hopefully you've noticed that the x values are powers of 3, but then they are going to be doubled. But we'll talk about that again in another problem. All right, let's figure out our next k value. So from 4 to 5, from 5 to 7, from 7 to k, this one is obviously a little bit harder. And I don't like how they are kind of explaining it, but can we come back to this? Let's do this together in class tomorrow. I need to find a better way to explain this problem. Okay? Same thing with this last one. We'll come back to this in class. All right. And then the last example is finding the domain of the following logarithm. So remember that with log functions, they do have a restricted domain at 0, even if a is negative. The only thing that's going to affect this domain is moving left or right, okay? So it's a movement of left or right. Now, based on these three problems, the only one that there is a movement of left and right is this guy. So this is g of x is equal to -5 log base 2 x minus 3. So this one we can say is moving right 3. So if there's no movement, the domain does not change. It's from 0 to infinity. And the range never changes, even if there is an up and down movement. It's from -infinity to infinity. So the range for log functions will always be -infinity to infinity, -infinity to infinity. Because even if you move up and down, it's still just going further down and further up. But the domain does change based on the left and right movements. So if this guy's moving to the right 3, that means that 0 is changing and moving to the right 3. Or the vertical asymptote that was at 0 is now moving to 3. Okay? This guy right here looks like this. H of x is equal to 8 log of 2x plus 3. So again, there is a left and right movement. And what is that left and right movement? You remember that you have to factor out that 2, and you're left with 3/2. So what is the movement here? It's going to be left 3/2. So instead of the vertical asymptote of that log function being at 0, that vertical asymptote is moving to the left 3/2. So our new domain is going to be -3/2 to infinity. So the only thing affecting the domain is going to be a left or right movement. Nothing affects the range. All right, enjoy.